we'll take a look at some more examples. Examining some more complex molecules, CH4O, which is methanol. What's the Lewis dot structure for methanol? We've got one carbon, 4 hydrogens, and 1 oxygen. How do you arrange all these elements so that they're arranged correctly, all the covalent bonds are correct? Usually, trial and error. You keep arranging them until they are right. So let's consider how many valence are in carbon. 4 valence electrons in carbon. And then we're going to add that to the valence for hydrogen. Hydrogen only has 1 electron, but there's 4 of them. And we're going to add that to oxygen, has 6 electrons in the valence. 4 plus 4 plus 6 equals 14. The molecule we construct should have 14 electrons in the valence. So this is the structure I put together, and we want to check to make sure that it's right. So starting with the hydrogens, right? The hydrogens will only have 2 electrons. So hydrogen is bonded to carbon. The line representing 2 electrons. So each hydrogen has 2 electrons. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. He's good. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. He's good. And we want to make sure that the entire molecule is correct. You should have 14 electrons. So we count all the electrons. One line equals 2 electrons. 1, 2, 3, 14. There is another way to arrange this, and you notice you'll do it one way, it'll be wrong. C2H3F. 2 carbons, which gives us 8 electrons. 3 hydrogens give us 3, and 1 fluorine gives us 7. We should have 18 electrons in the valence when we put together our molecule. The structure I put together is 2 carbons that show a double bond. Hydrogen has a single bond to carbon. A single bond is a sigma bond. And then when you have a double bond, it's considered 1 sigma and 1 pi bond. And what's happening is the electron clouds are overlapping and sharing electrons. Whenever you use fluorine, a lot of times fluorine likes to only have a single bond like this with all his lone electrons sticking out. And we want to get to 18. 1, 2, 17, 18. 18 electrons, the structure is right. The next compound is phosphate trichloride. And our phosphate is in the 5th column. He'll have 5 electrons. And there's 3 chlorines, which have 7 electrons, totaling 21 plus 5 is 26 electrons should be in our molecule. And our molecule will have phosphorus in the middle. And you can draw as 5 electrons. When you first start drawing Lewis dot structures, you should start and draw everything out. And you might draw a wrong compound and notice that your valence electrons don't match how many should be in the valence, but it's trial and error and practice. And so I matched up the single electrons with phosphorus, and they bind like this. Let's examine the polarity of this compound. Remember, chlorine is an electronegative species, and relative to phosphorus, it's more electronegative. So his electronegative arrow is pointing in this direction, and one is pointing down, and one in this direction. I've got one electronegative arrow pointing right and one pointing to the left. Therefore, these 2 arrows cancel each other out. But I still got one arrow pointing down, indicating that this is a polar species. Lewis dot structures are very helpful in showing us the shape of molecules. The valence shell repulsion theory shows us a list of many different shapes, which is quite easy. You look at the chart and memorize the shapes. This particular molecule, phosphate trichloride, will form a shape like so. The two lone pair of electrons on the phosphorus create a shape to where this chlorine is coming out towards you, and then the broke line shows that the chlorine is away from you in space. And the bond angle between each chlorine, the position of these molecules also influence the reactivity when mixed with other elements. So it is important to consider the shape of it's important to consider the spatial arrangement of electrons.